and I'm happy to be here to introduce the first one. There will be a small break between the two seminars with the famous pizza. But before that, you heard the quotation mark. But now it's time to introduce the first of the two speakers, Benoit Vermersch. Benoit Vermersch from University of Grenoble, and also as in what do we say? It's appointment, or how it's called, this temporary appointment, or at Quobly. Okay, so Quobly is a company that is developing spin qubits in silicon, so quantum computing technology, and so Benoit has a very nice, very fine track in quantum that brought him from the University of Lille, where he got his PhD, to the group of Peter Zoller for quite a long time. So you have a strong influence from one of the cradles of quantum. And since 2019, you are professor at the University of Grenoble, and you are also probably since more recently you are also in Quobly. And your the talk will be on randomized measurement for large-scale quantum experiments, and I'm looking very much forward to your presentation.
Thank you, Vincenzo. Thank you very much for the invitation. It's a pleasure to be here. It's actually the first time. Not so far, but I didn't have the chance to. Very often I travel to Innsbruck, to Lausanne, but I didn't stop there for a moment. I decided to present kind of an overview of our activity on randomized measurement over the last, I would say, 8 years now. First, it was some kind of a theory, a proposal, and then over the years we could apply this in different experiments. And today I would like to focus on the experimental part and give some hints about what we had to do on the theory side to kind of follow on the experimental progress. In this experiment, having more and more qubits, we had to change our formulas over time to be able to measure something interesting for this many qubit system. That was the idea. Just a word about Quobly. It's now 4 years that we have Quobly in Grenoble. It's a spin-off of CA and CNRS. So as you probably know, there's a long history of condensed matter studies in Grenoble, both from CA and CNRS. And the goal of Quobly is to kind of use this experimental platform to form qubits based on electron spins. And we are now about 100 people there. And our part is the quantum information part, which is 6 people plus me, and we are interested in the theory part of Quobly, so we
some rooms that switch to.
So we have basically 3 topics of interest. The first is compilation. So we are given a set of possibilities for the hardware in terms of what we can vary with time and control, and we are trying to see how we can synthesize arbitrary quantum circuits based on these native elements. This is associated with an open source project SpinPulse, which is now available online, and we have Marta and Julia just here as members of this effort. We have a simulation activity which is called QSE toolbox. The goal is to study quantum algorithm for the fault-tolerant era. So having logical qubits and so on, and trying to perform resource estimation to analyze how many qubits we need and how much runtime we need to implement application for quantum chemistry. An important focus of this project is to use tensor network to try to, at the same time, synthesize the quantum circuits, load approximate solution of quantum chemistry via the DMRG algorithm, and also simulate for a few logical qubits as much as possible. And we have the benchmark activity, which will be the focus of this talk. How can we extract relevant information from a quantum computing experiment, and how we can make statements about robustness against noise, ability to create entangled states, and ability to produce quantum states which are challenging to mimic classically, for instance, tensor network methods. And we have also an open source project which is called Randomized, which I will discuss today in more detail. Dimitri is a PhD student for this effort. He's formerly employed by PSI, and he's registered at EPFL, so we will have a chance to see him around. Okay. So for today, I will first review some concepts of quantum info that I need, in particular entanglement and measurement. Then I go through the concept of randomized measurements from the first ideas to the first experiment, then the second ideas and the second experiment, sort of. And I will conclude with two recent proposals to apply randomized measurement and large-scale experiment, and also describe the corresponding experiment which occurred at IBM. So feel free to interrupt if something is not clear. So for what I need to explain, I consider very typical quantum computing system. Okay, so I have n qubits. If the system is ideal, it's completely decoupled from an environment. I can describe it by a wave function psi of 2 to the power n amplitudes. Okay, and we describe this wave function as a tensor with n indices. Okay, S1, S2, so on, Sn. We know and we hope that in quantum computing this object will not be trivial. For instance, in general, I will not be able to write psi as a product state. Okay, so this means that this is called entanglement. I'm not able to write psi as a product state, and I can actually prove that if the state is not entangled, it's classically simulated. Generalize this expression to n parties. So to do something useful with a quantum computer, it's a little bit of a trivial statement, but we need entanglement. And I can also say that if I prove that the system is entangled, I can preserve the hope that I will be able to do something useful with it. So that's why we are trying to measure entanglement, what we did over recent years. The second important object for me is the density matrix rho. In general, the quantum computer is not isolated. It's never completely isolated. And I need to introduce the object, the density matrix rho. And an intuitive picture for a density matrix is that if you have just classical noise on your system, you can think that instead of realizing a single psi, you will realize a stochastic mixture of different psi r. And the density matrix then is simply the average over the projectors over these different psi r. So that's connection between pure and mixed state, if you want. If you know the density matrix, you know everything about the system. In particular, any expectation value is a contraction of the density matrix with no Hermitian operator O. So that's the first statement. The second statement is that you can contract the density matrix with itself. You obtain trace of rho square, which is called the purity, and it's called the purity simply because it's one if and only if you can write the state as if the state is pure. You can write it as rho psi psi. So that's the density matrix, if you want, of the whole quantum computer. Now, typically to describe entanglement, we also use reduced density matrices, which are obtained by tracing the density matrix rho over some part of a system. So if you trace over B, you obtain the density matrix on the system A, which is the remaining part. And this is the density matrix of the system A in the sense that it satisfies this equation for any operator having support of A. So that's a consistent definition of the density matrix. And now, with this object, we can study entanglement. In particular, I will need to define entanglement for pure and mixed state. So for pure states, it's simply what I wrote before. A state is entangled if you cannot write it as a product state. For mixed states, it's a little bit more complicated. We cannot write the state rho as what is called a convex sum of density matrices of the form rho A tensor rho B. But you can keep this intuition that it's kind of a product state structure. Now let's try to quantify entanglement with density matrices. Because if I can quantify entanglement with density matrices, I will be able to measure entanglement based on measuring something about density matrices. I take a pure state for this case. I can always write a Schmidt decomposition, which is a general decomposition of a vector, if you want. It consists in writing psi as a sum of product state, and these ck are complex numbers. And you can see that if I have only one ck, the state is a product state, and if I have many ck, I can understand that the state is more and more entangled as the flatness of this distribution of ck evolves. Now I can look at rho A. Rho A is the trace over B of rho, and I will find immediately this expression that rho A is the sum of lambda k being the square amplitude of the ck. So the lambda k, if you want, are the eigenvalues of rho A. So if I can probe the spectrum of rho A, I can probe entanglement. If rho A has a rich spectrum, it means the state is very mixed, and the state is the pure state, the underlying pure state, sorry, is very entangled. And to quantify a spectrum in terms of distribution, we look at entropies, as usual. We can look at Renyi entropies, which is a function of rho A in this form, that I can write as eigenvalue lambda k. And I can use the second Renyi entropy, which is simpler for me, which is the log of the purity, the minus sign. And you immediately see that if I have only one lambda k, the entropies are 0. So if I have no entanglement, entropy is 0. And then you can see that if lambda k tends to be flat over the maximum number of possibilities, which is Hilbert space dimension, the entropy will be D, Hilbert space dimension. So I have somehow a measure to tell me how many product states I need to quantify entanglement to describe my pure state. And this is the quantity of interest for research. Okay? Just a remark, but more formally, in quantum information, you can prove that these entropies are faithful entanglement measures in the sense that, for instance, they cannot increase over local operation and controls, this is called LOCC. This is for pure state. Yeah, I was just describing pure state. For mixed state, everything is more difficult, in particular to quantify entanglement. There do exist entanglement monotons, those quantities which do not increase under local operations, but this is not the entanglement entropies. One example is the entanglement negativity, which have a different expression compared to these ones. But maybe later or another time we can discuss how we can apply our ideas to measure this type of quantities. So that's quantum info statement. In terms of many-body quantum physics, entanglement entropies are also studied. And very often you can show that they have universal scaling behavior in ground state of many-body systems or in non-equilibrium quantum dynamics. We will see an example later. Okay? So that's an intro on entanglement. And now I have a very short intro on measurement. Very, very short. Okay, so how do we perform measurement in a quantum computer in the standard scenario? We have our n qubit here. You do whatever you want on this qubit. This can be a perfect circuit. In general, this will be its noisy counterpart. And the measurement step is described here. You simply measure the qubit in the computational basis. So you ask the qubit, are you 0 or 1? And you obtain an answer, which is called a bit string, which is a list of 0 and 1. And we know from Born rules that this bit string is obtained with probability S rho S. So repeating this many times, you will build a histogram, which will be this probability, 1 to 1. Every experimental platform does this. Obviously, this is a requirement for a quantum computer. I want to emphasize that these experiments, at the moment, do this very well. We can measure typically from 1 million to 1 billion times a given quantum state. So the kind of experiment is stable over, allows you to measure this number of times before the states of the experiment needs to be recalibrated or changed. Okay. So then the million is typically what you can do with ions or cold atoms, and the billion or 100 billion is more for the superconducting qubits, which are experiment of the kilohertz machine. Last thing I need to introduce for measurement is typically that we cannot be happy with only measuring in the computational basis. So very often we apply qubit rotations. So these are single qubit gates prior to the measurement. So if you look at Born rules, in this case, you sample bit string according to the rotated state u rho u die. And this allows you to probe the state if you want in different bases. And in current experiments, you can see different measurement settings. So the number we have typically with ions is 100 recalibrations, measurement settings, and with superconducting qubits, you can have even 10,000 different single qubit rotations applied on the same quantum state, which are, I think, remarkable technological achievement on the measurement side. We have this extraordinary list of bit strings we can now analyze, and it's now many groups playing with these bit strings over the years and trying to use this enormous data set of millions of bit strings to tell something about rho. That's the game we are playing at the moment. And it's been very interesting. So without a quantum computer, you would never do it. Okay? So if you think of the old days of quantum simulation with Bose-Einstein condensate, where you have one bit stream, one image per minute, this you could not play with it. So that's something which I'm very grateful for. Quantum computing effort, that you can play with this measure. Any questions so far?
This NU,
Yeah.
what's NU here? What do you mean by?
So I will typically measure for one choice of U.
Yeah.
I will obtain a histogram according to this bound probability. Then I will take a different U. So I will sample this nucleus.
What is this like in a certain amount of time? Like what's limiting you from just continuing by doing single qubit rotations?
Well, it's, at the moment, at some point, the experimentalists don't want to measure anymore. So if I ask my untrapped friends to measure for more than 1,000, they complain because they want to measure in say 2 days or half a day.
Okay, so it's a time that takes to change the gate.
Exactly. It's not a physics concept. It's
You're
more.
assuming a certain number of shots on each U.
Yes. Typically, for ions, you could have 1,000 shots per U. And if you would do 100, this would take the same time, more or less, because when you change the U, you need to perform some checks that you don't need to do between each shot. So the total runtime of experiment is a function of both NU and the number of shots. Always have the discussion with the experimentalists.
No, that's fine. Like IBM initially didn't allow you to easily just change the final U. So you used to have to give in batches of different circuits.
Yeah.
And so there's a big gap between batches.
Yeah.
But now they've added a capability specifically targeted for like shadow-like seams. Because they
Yes.
say that actually recompiling into the final data will take too long.
Yes.
And maybe they don't do all their recalibrations when they just change their final one.
It's an excellent concept.
So I think now for them, if as long as it's just the final layer, they're not too restricted. It's still a bit of a restriction. You play games where you don't fully randomize them, but it feels less restricted.
Yeah, I agree. So with the new version of IBM, you can transpile one given circuit for all the use. That's really different.
Well, wait, so you're talking about your spin systems here when you're saying, this is your group that's saying 10 to the 4, is that it? Or this is...
So I will discuss experiments today for superconducting qubits performed both at Google and IBM. Not explain qubits. Last statement I want to say is if you have such a possibility of measuring, we have what we call an information complete measurement protocol. It's possible in the limit of infinitely many measurements to reconstruct exactly the density matrix rho, so to measure entirely the system. One way to see it is that you can write rho as a sum of Pauli operators, because the Pauli operators are complete basis for this Hermitian matrix, and you can show that all this expectation value trace rho sigma can be obtained by mapping the computational basis, so the Z basis, to any Pauli basis via a simple Clifford transformation, which is a product of local single qubit rotations. So we know we can measure the whole density matrix. The question will be efficiency. The only question which matters is efficiency. How many measurements do we need to measure a given quantity? And if you want to measure the entire density matrix rho without making statements about the structure of rho, you need to measure 4 to the power n matrix elements. And to measure one given matrix element, you need to perform a measurement of trace rho sigma with many shots, potentially 2 to the power n, because these expectation values can be very small. So overall, we don't do state tomography in general for more than 8 to 10 qubits. If you want to go to larger systems, we need something else. which will be purpose of the second part, which happens now. Okay. So this was a long story, and there are now many groups working on that. In my case, I really want to acknowledge Peter, who kind of suggested me very strongly to work on this. And first, I hated it, like it was my postdoc was a duty, and finally I enjoyed it. Andreas was a PhD student with Peter, and is now a very, very good friend. He's at PSI, and we continue collaborating over the years, and we have many, many people who participated. The Caltech team proposed incredible proposal on the theory side, which somehow boosted the field to an incredible level. I will mention the work of Matteo, my former PhD student on tomography, tomography with randomized measurements. And I also would like to thank the experimentalists, Xiaomi from Google and the people from Innsbruck. We could do randomized measurements on the theory side because some experimentalists were brave enough to try and to measure millions of bit strings, sometimes during many hours. So randomized measurement consists in taking the circuit of tomography by analyzing the data differently. Okay, so I have my quantum system. I have whatever circuit. The measurement step is the same. It's just that I will choose the random rotation ui randomly, independently of what I want to measure in the end. I will just do always the same acquisition. I will do this for many u, so what I call nu, and many shots. And the goal is to analyze the statistics of the bit string. So it's a very simple goal. And we kind of analyze in the review what are the goals, and in which case you can prove efficiency, and in which case you can prove that it's not efficient. The good news for experimentalists is that it's in principle simple. You will take to measure. The first of kind of important equation we were able to prove in our case, which was a follow-up of works by Benoit, is that the purity, which I introduced earlier, is a direct function of the statistics of randomized measurement. That's the formula here. So on the left-hand side you have the purity, and on the right-hand side you have an ensemble average. So this is ensemble average over mu of the quantity which involve the histograms of the measured bit strings for a given u. So you will measure the histograms, pu of s, and then you will study some of the segment moment of these histograms by taking the ensemble average. And this is exact. This follows from random matrix theory. For the expert to see that you have 2u here, 2u tag, so you just need to use two design equations to prove this equality, and this is why we were able to do it. Because we can only manage two design in the team. And immediately you can see, if you study the protocol, for instance, numerically, that you can access, with the type of measurement budget that I showed earlier, you can access purities in systems which are about 14 or smaller. So it's an equation which is practical and which could be used experimentally. And I would like to show just one example of a recent demonstration where this number 14 was important, or 13. It's the observation of the area law of entanglement, which is a conjecture, very important conjecture in condensed matter physics about the structure of entanglement in several spatial dimensions. So let's take 2D. In 2D, if you consider a standard Hamiltonian with local interactions, it is expected, it's a conjecture, but the system has a finite correlation. So if you take a qubit here in the corner, it will not interact with qubits which are far away. Okay, so some notion we can understand intuitively. So let's try to count how many qubits of the partition A are entangled with a complementary part B. Then you will see that the qubits which are most likely to be entangled with B are the ones which sit with the boundary, because the one in the bulk are too far away from the boundary. And if you take this simple statement, you will see that you will expect that the entanglement entropy, so if you want the number of entangled qubits, will scale with the area of A, which is in 2D it's just this boundary, order 5 to 6. And this is unusual. If you take a random state, you will expect that everybody is entangled with everybody. You will have a volume law. The entropy of the system will be equal to number of qubits, volume of A. And to see this effect, you have a finite size effect. So you need a system which is quite large, of the order of 9 to 10 qubits. And you need to be able to resolve a different type of scalings between area and volume. So that's challenging for experimentalists. So Google was brave enough to try. They have the sycamore that you know very well. What I learned then is that they can also operate the sycamore in an analog mode. So instead of having 2 qubit gates on and off, they just switch on all the couplings simultaneously. And then the system is described by a so-called 2D XY model. You can just think of all couplings on. It's an Hamiltonian, and you can play with the parameters of this Hamiltonian to prepare the ground state adiabatically. And then they observe a transition from area law with the ground state, which is in blue, to volume law for excited states. And this is, for me, the best experiment for randomized measurement, because it was in a regime where you need large system sizes and you need excellent statistics to see this, because this, you see this entropy of order 12. This corresponds to measuring purity of 1 over 2 to the power 12, so 1 over 4,000. So imagine the cost in terms of absolute error. You need 1 over several, more than 10,000, yeah? And this is why they needed to have, in this experiment, 100 million discrete measurements. So that represents a massive experimental effort. So, you need an excellent system to prepare quasi-pure states, and then you need to measure a lot to observe this area law quantitatively.
So they were working with single qubit 2 design, I guess, and so measuring the poles of the block sphere to stabilize the states.
Yeah.
And they did each of the measurement settings. They did. No, that's too many. So they randomly picked some until they had 10 to the 4 different random settings, and then they did those in chunks.
Yeah. They did a uniform sampling, or 10,000.
Okay, so they
10,000 seconds.
10,000 seconds.
Yeah. I think I can check.
Do you know how much that then deviates from the solution you would get if you were actually picking each one?
That's I think they analyze this effect for small system size, and it's not so much. What you shouldn't do is to apply tomography blindly and calculate trace rho square of these tomographic measurements, because then the estimation of purity will be biased. It's a quadratic quantity. But if you sample all these strings and fix the bias, I think it's not so much effect. Other questions? So this experiment for me was very important because it kind of prove that we can fight statistical errors to a very good level. And now it's time to recall that measurements always are subject to also to systematic errors. When you are measuring a qubit, in any platform you have a measurement errors, which is here highlighted with this quantum channel lambda. And all your estimations, if you kind of ignore this measurement channel, will be biased. But the good thing is that you can correct for this bias using what is called robust classical shadows, which is a new formalism where you are using, instead of one single round of randomized measurements, you are using two. And for the first one, you are using a state that you know already, typically all qubits in 0. And by cross-correlating these two experiments, you can obtain unbiased estimation of the density matrix and of the purity based on this formalism. So that's the experimental sequence, not so much different. And the theory, the post-processing, is now very different. And it's an idea at the beginning from Caltech, that taking your bit strings, you can construct an object which is a tensor product, which has a tensor product form. So you can store it easily on a classical computer. And this object involves a bit strings, the measurement settings U, and it also involves fidelity F, which is a quantity that is accessible through this calibration step. And again, using tool design theory, you can prove that this object is an unbiased estimation of the density matrix. And based on that, estimation of any quantity will follow. So I will not really describe it now, but this is very convenient to form this object, because then you can access anything that you want, more or less. So we kind of proposed recently Julia package, right, to no, it's Python. A Julia package to post-process randomized measurement with classical shadows, including robust classical shadows. And I like it because you can, at the same time, simulate randomized measurements with fake data. And when you are ready, you can connect to IBM and then try to see if you can measure the purity, for instance, and play different tricks. I mentioned robust, but there are many other tricks, statistical tricks, that you can use. Okay, so now maybe for the last 5 minutes or less.
Okay, less.
Yeah. Okay. I can flash two recent ideas to operate randomized measurement in large-scale experiments. This was a collaboration with Peter and Matteo. My former PhD student was essential in the second project for the tomography. When we are trying to apply randomized measurement ideas in the large-scale scenario, and in this case, the situation is a little bit more complicated. I will not be able to construct directly estimators which are efficient for measuring properties of a very large system for clear statistical reasons. But what I can do is try to apply these ideas on many subsystems, and I will try to propose formulas to combine this measurement on small systems to construct estimation for quantities of a global system. It's called a quantum marginal problem in quantum information. So this work I cite here. The idea is the following. If you have a system with a finite correlation net, so many-body systems, typically when you measure C, which is here on the right-hand side, you will never affect much the state on A. So there is no correlation between A and C. This is quantified by a quantity which is called conditional mutual information. And we know that if the conditional mutual information is 0, we know that the state of ABC can be reconstructed from marginals. You only need to measure AB, BC, and ABC separately, to express rho ABC as a density matrix. The question is, how do we apply this idea to randomized measurements where we don't measure the density matrix, we measure functions of the density matrix. So this is the work we did with Peter and co-workers. And we took a toy model for a system with a finite correlation length, which is a tensor network model where you can write the density matrix as a product of tensors, and you can prove that there is a correlation length in such a density matrix. And dealing with this object, we prove an equation which is here, which relates the purity of the total system to the purity of the subsystem. Therefore, it's a solution to the quantum marginal problem. And what do you do with this equation? You state that in order to measure the purity of a total system, I will measure all the purities of the subsystems, I will multiply these numbers, and I will get the total purity. And you can do the error propagation for statistical errors, and you will see that you will be able to measure the purity of large systems with polynomially many measures. That's the statements. And now I jump to experimental result. Just to show one example, but for a system at IBM, but you will get the same everywhere. You can take 100 qubits, you can apply this formula, you will see that the purity, that's a reverse log axis, okay? You will see that the purity of 100 qubits is about 10 to the minus 4. You get probably 10 to the minus 3 in the Chiron device. So the question for you is this good or bad? Is this small or high? I would like to state that it's a high number. Okay. Because if you will have a maximally big state, you will have 1 over 2 to the n. Okay. So perhaps it's simpler to understand this in terms of entropy. The entropy of a system of a state which are produced is of order 14. The maximum value is 96. Okay. So the claim is that this measurement claims is a many-body state which is 75% quantum, and this is verified logistically. That's my conclusion. We have some more nice tool. We play with statistics and assumption on the state that we can verify, and now we can apply this in the large-scale scenario. And many open questions about error mitigation. What do you do with these measurements? Can you probe crosstalk? Can you recompile? All that is ongoing and very exciting. Thank you.
It's very exciting results. Any questions or comments? Please.
So the main purpose of randomized listening is to test the statistical distribution, or the main goal is to test the statistical distribution with the randomized listening.
The goal is to measure physical quantities, I would say with known error bars. So you give me, say, the purity, I will be able to provide you with a formula, and if you are an experimentalist, right? And I will be able to tell you, if you measure 1 million times, you will get your number accurately. Standard measurement task, but for quantum quantities.
So like the t-test, you decided the sample size.
T-test, I don't know.
I would say it's a way to choose the measurements in an optimal way, so to have the least possible number of measurements to get sufficient statistics.
I wouldn't say it's optimal.
It's not optimal, but it is towards. Yes.
It's probably optimal for some fixed states you don't care.
Yes. If you have a state which is very structured on the basis, you will probably spend more time measuring there. But if you don't know anything, yeah, well, it's okay. Not so far.
The other question.
Going back 2 slides, think, 2-ish. No, one more. No, oh God, that one, yeah. Okay, so, oh God, I might even be the wrong spot. Basically, I want to understand the link with the marginal problem. So, there is the quantum marginal problem. If you have the marginals, you can't recreate the whole state. I guess that's not inconsistent with what you're saying about purity, because you're not recreating the whole state of purity. And when you said mutual information, does that also apply there? What can you recreate?
That's a good question.
Yeah, I think previous slides. What do they say about?
This statement here is on the condition of mutual information expressed with von Neumann entropies.
Yeah.
With this log, but we don't like in randomized measures because we are not able to provide unbiased distribution.
Yeah.
So we want to generalize, if you want, this solution to the second Rényi entropy or purity. If you take the log on both sides, you get something like the Rényi combo. The condition of mutual information is approximately 0, and the systematic errors can be estimated from, in this case, for this problem, you can relate this systematic error, so if you want the finite value of the conditional mutual information, to the correlation length of your LPO, which is 1 over beta 2, where beta 2 is, I think it's the gap of the transfer matrix. It's the correlation length of the LPO. 1 over.
I've seen this expression before, I think. But I'm not it's a very basic question. Actually, I missed what the bracket E means.
E means estimation. We measure in an experiment this estimation. It's not the purity, it's the estimation of purity from accessible to randomized measurements.
So then why is there not an but that's in the limit of infinite n? Otherwise there'll be an n that would appear somewhere like the number.
It's the limit of infinite k, which is higher. So what happens is that I will divide my system in blocks of size k. I'm able to provide an expression for each block size k. This will converge as k goes to infinity to the exact purity. And
with enough shots, though. With enough shots, n or like some average somewhere.
But even if you have infinite shots, if k is finite, you still have an error because the conditional mutual information is not strictly 0. It is it decays exponentially to 0, and that's the decay.
What was the depth of the circuit on the IBM chip to achieve 10⁻⁴ estimated purity?
So the depth 1 or 2 is already counted, but it's each pair of qubits was an entanglement.
Yeah.
So on this difficult 1, we use the difficult 2.
So you just made a layer in which you applied to every pair of to every connected pair of qubits. Okay.
It's a state which is classically simulatable.
Yeah, that was going to be my point. Is that I mean the heavy X is if you write it as a tensor network, it is almost an MPS. So this thing can be written as an MPS plus very few, so to say, bit longer distance. So how does this affect your technique? I mean, suppose you had an octa-core quantum computer. Would you?
So actually, it's even worse. I implemented a strictly one-dimensional quantum circuit by killing some couplings. Right?
Oh, okay. So so there is a strong assumption in the quantum circuit. Okay.
We would like to try in 2D. We believe the quantum marginal problem is also solvable in 2D. We are just scared that we will need, if we need a factor, if we pay an overhead of 100, we cannot do this experiment. Of course.
You talked about military to design. Do you have any assumption on the to use military to design?
So I need to sample the U from a unitary to design.
Okay. It's just, this is, the U should be sampled from
Yes.
some unitary.
In practice, we use hard random unitaries, but you can use also Kiefer.
Okay, I'll take the last question before the pizza. Please.
Can you comment on like experimental implementations of these randomized measurements when using global unitaries instead of local ones?
Yeah.
Like what is the state of the art, and are there recent experimental demonstrations of these things?
With global, I think I've seen one or two. One with NMR. What IBM did recently is random unitaries generated by shallow circuits. So it's between local and global. You have the finite depth quantum circuits, where the 2 qubit gates are random. It can provide an advantage if you're interested in some low weight observer. The problem is that very often you need to construct the classical shadows. You need to do a numerically tensor network optimization first, at least. You can do it, but it's painful.
Okay, so I would say we go to the pizza. So thank you very much, Benoit. Who's in charge here of operating the pizza container before? Okay, I don't want to do this. Is anyone?
The trick is not to make eye contact now.